So we're going to have to bias the two exponents and also add them together. So let's go and we'll start doing that now. So we'll start off with a circuit, and we'll call this circuit FPU underscore bias x plus y. So we'll build our circuit in the main section and then we'll shift it over into here. So let's go into main, and we'll start off by putting in a couple of input pins. So this is going to be facing east, and we can call it FPU underscore x, and the label will be facing west, and it'll have to be an 8-bit input. And we'll do the same for the Y pin. Y, actually we'll call those XE and YE. So this is going to be, the bottom one here will be YE, and the top one will be XE. So that's the exponent for X and the exponent for Y. And the output here will face the label east, and that will be the output, which will be the exponent for X plus the exponent for Y. Y exponent. Okay, so we've got our two input pins and a single output pin. Now, in order to find the values here, first of all we're going to have to bias it. So in order to bias it, we're going to take the 127 from it. So you can get into the arithmetic section here and pick the subtractor, place the subtractor down, and the same for the Y value. And we want to subtract off 127. So in order to subtract off 127, we go up to the wiring section and we pick out a constant. And our constant is going to be 8 bits. Now the constant value here is given in hex. So if we want to get the number 127, it's going to be 127 in hex, which is the value 7F. Okay, and I'll face that east. So the best thing to do, if you're unsure about the conversions between hex and binary and so on, is to get into Excel, and they've got simple converters there that will allow you to convert. In fact, we'll show you that just in a minute. So we've got 7F here. Okay, so this is allowing us to subtract the 127. So we should get an output here. Now again, the best thing to do is to check this as you work along. So if you get the probe, face it south, and you can get the other probe. In fact, you can run that right up next to it like that, so just keeps it neat and tidy. And get another probe here, and we'll face that one north. And the probes here, you can change the radix in it. So at the moment we'll just put it in as unsigned decimal. And of course we're going to have the output here, so we'll copy this. And copy this one. So if we were to put in a number here, and you see that this here is going to be the number 128, so it's 1, 2, 4, 8, 60, 32, 64, 128. So that's 128 minus 127 will give you a value of 1. And again, if you put 128, you take away 127, you get a value of 1. So that's subtracting off OK. So after the subtraction, we're going to have to sum both of them up. So we're going to go in again to the arithmetic section here and go to the adder. I'll stick the adder here. And we're going to get our input here and a second input here. Take it here to the output. And of course the adder has to be an 8-bit adder. And we have the output pin, but the output pin has to be an 8-bit output pin as well. So you can see here, if we were to put the probe in fact you don't even need to, you can see here there's 1 plus 1, and in binary 1 plus 1 is 2, but again you can put the probe in here. And you can see the summation is 2. So that's a very easy little section to put together, but there is some little nuances in it which we'll get into just in a moment. But watch what happens whenever we change these numbers. Now it'll make it a little bit bigger, you can see it a bit better. If we were to change this number to, for example, the 2 and this number to 2 here, then we're going to have the number 2, and whenever we subtract off the 127, we're going to end up with, well, this number here, which is 131, but 2 minus 127 is not 131. So what we can do is we can actually click on this, and if we represent it as a signed decimal, then we'll get the correct answer, which is minus 125. So a signed decimal will get 125. So that's going to be 2 minus 127 is minus 125. But now what we're going to do is we're going to add both of these together. But if we were to add minus 125 and minus 125, then it's going to be minus 250. But the signed decimal will only run up to minus 128, so we can only get values up to minus 128. So when we go to add both of these together, we're going to end up with the summation here will give us an overflow, and we'll be left with, in this instance here, we'll be left with 6 at this side, because we'll be left with 6 because we can only go up to 128. So we're going to have an extra 3 from here, and we would end up with an extra 3 from here, so that would be the positive 6. So we have to be careful how we use these signed and unsigned terms. And again, you can see this here, if you click on this and you go to the unsigned and you go to the unsigned, you can see still we're adding 262, so 262 is going to be above the threshold for an 8-bit number, which is going to be the value of 255. So it's going to be 6 beyond, and this is the extra 6 that we can see here. So we have to be careful how we interpret these numbers of signed and unsigned, and whenever we do the additions and subtractions. So let's have a wee look at this in a spreadsheet. So if you open up the spreadsheet in the resources section and you go to sheet 1, so I've got the FTD here and we've got the sheet 1. You see here that I've put in the numbers 0 to 255. Okay, so that's in effect, there's 256 altogether, including the 0. And this is representable in 8-bit binary, and this is the 8-bit binary representation here, so that's the normal binary that you're used to seeing. It goes from all zeros up to all ones. So we can change that here very simply in Excel using an Excel function, which is equals decimal to hex, and I just put in the particular column, of particular cell is A2. So we'll just change it here from the binary here to the hex, and you can see the hexadecimal values. Now the unsigned integer is something called the sign and magnitude. So in order to count up from 0, you'll see it counting 0, 1, 2, 3, all the way up to we get to the number 127. So 127 is the value 7f, and this is all ones apart from the first one, which is 0. So the first 0 represents a positive value, so that just tells us that what comes after here are positive values, and we can only go up to plus 127. So now after 127, the next number along here is going to be 128. But what we do in the sign and magnitude is that the 128 is defined as being negative, so this is actually minus 128. And then this would be minus 128 plus 1, which is minus 127. And then it would be minus 128 plus 2, which is minus 126. Minus 128 plus 3, which is minus 125. And so on and so forth, all the way down until we get to the value of all ones, which will become the value of minus 1. So when we look at the probe in Logisim and we change it to sign decimal, then the sign decimal is the value that we see here in column D. So we just have to be careful that we do understand the values that we're looking for, and why it is sometimes we might get results from a comparator or an addition or subtraction that we weren't expecting. So let's continue building the sum of the exponents. Before we go on to create the instance for this, we'll put a little note in so that we can remember how this is actually working. So we're going to have minus 127, which is the exponent bias, and I'll make that 16 and I'll make it bold. Okay, well, this one here I'll make it 16 and we'll make it bold. So that's how we get our bias, and then we're going to have to add the exponent, so we'll put this over here. So this is us summing both of the exponents. Sum of the exponents. So let's grab our circuit here from main. We'll go Control X and we'll put it into our bias x plus y. And now we'll go ahead and we'll create our hierarchy for it. So project, edit circuit appearance, and we'll pop it in and we'll put this together. So we're going to have the output, that's the x plus y, and we're going to have both the inputs. So we're going to have the x input and we're going to have the y input, and we'll just type the names here. We're going to have our x, e, y, e, and we can call the outputs here is going to be xe, and we'll just call it dot, let's call it plus ye. That's our xe plus ye there, and we're going to have our xe, we'll have our ye there. And again, we'll give it our name, so we'll call it the bias and x plus y. And we'll make these bold and 16. And we can position them here. So bias x plus y. So that's the first part of our little exponent. So let's continue with this. So let's go into main and we'll grab one of the biases here. So this is a block that we just built, It subtracts off the 127, which gives us the exponent bias, and then adds both the exponents together. So we might be thinking that this is us done with the exponent section, but there's a bit more to it. The exponent can be changed in two other ways. So we'll go into that just in a second. So let's open up, and we'll open up Smooth Draw. So these are the two ways that the exponent can be changed. There's going to be a shift in the exponent, or a potential shift in the exponent, and it could shift from, in this example that we've been using, from 2 to the 7 to 2 to the power of 8. So it could move by a factor of 1. But don't worry about this just now. We'll get into this whenever we go to the multiplication of the mantissa. For the moment, all we need to know is that there's a potential other way that the exponent can change. So that's one of the ways. Now the other one is in the rounding. So in the rounding, we're going to use the nearest neighbour rounding. So it means that we've only got 32 bits. But what we're going to do is we're actually going to look at the 33rd bit. Now if the 33rd bit is a 0, then we can just drop it. And in effect it's like just rounding down. But if the 33rd bit is a 1, then what we can do is we can carry that 1 potentially up over into the higher order bits. So what we do is we look and see if the 32nd bit is a 1 and the 33rd bit is a 1, then we're going to carry that over. So that's in effect it's a round up. But if the 32nd bit is a 0 and the 33rd bit is a 1, then we drop, in effect we round down. So this is really a nearest neighbour rounding. So this will become clear whenever we actually go and build it in Logisim. But what we have to note here is that if we were to have an extra bit carried in from the 33rd bit and we were to sum it, and all of the other bits are values of 1, then whenever we sum it, that 1 bit could carry all the way up through all of the mantissa, and it can carry all the way up through into the exponent. So we have to take care of that single bit that can come up through. So let's go and we'll add that into Logisim, and all we'll do is create a couple of inputs, and later on whenever we build the circuit for the exponent shift and for the nearest neighbour rounding, we'll pass those values down into this block. So let's go back into Logisim. Okay, so we're in the main section here, and we've said that we're going to have to add in a couple of inputs. So the first one is going to be the shifting of the exponent. So we could just call that, if we want, we can call it, say, float, and we're going to add that value of float. So we need an adder. So that's our adder here, and we're going to add in a value that's going to come from some other part of the circuit. It's an input, so it's an 8-bit input, and we can just call this input float. So again, it's not a cop-out, we will explain this, but just not at this section here. It's not really expedient to explain it here. And we've also got another potential input, so we need another summer, and this potential input is going to come from a rounding. Okay, so this is going to be another input, and this is going to be a 1-bit input. Now the reason why I know it's going to be a 1-bit input is that obviously I've already built this circuit before, and I'm going through the rebuild of it again and explaining it. So the way I've designed it, this particular input is only be 1 bit. So this input here we can call round, and we'll make this west. But the thing is, if this is a 1-bit input, and this thing here, this adder is going to be 8 bits, then we're going to have to extend this from a 1-bit to an 8-bit in order for it to work. So we can't just stick this here because it's not going to work. And we can do that quite simply here by using something called an extender. So if we go to the section here, where is it? It's up in, yeah, on the wiring section. There's a bit extender. So we click on that bit extender and you'll see we'll be using these quite a lot. So this bit extender is going to go from a 1-bit to an 8-bit. So it just means that instead of putting in a single 0, it's going to put in, it would put in 8 zeros. So it allows us to connect it to here. So there's one other thing we're going to have to do in order to get the right answer, and that is add the 127 back on. So we Control C, Control V, and that's a summer, and we've got to add on 127. So again, we can grab the constant, and it's going to be 8-bit, and 127 again is going to be the value of 7F. So we take our 7F and we put that here, and that's going to give us our final output. So we can add the pins in here. So we're going to have an input pin, which is an 8-bit pin, and we can call this XE. And we've got the other pin, which we'll call YE. And I'll call that one YE. And we'll put these west, then we'll put that one there, west as well. And the output, which again is going to be an 8-bit output, and we'll call this EXP, and we'll put this east. So this is our final little circuit. So let's go ahead and we'll create a hierarchy for this. So we go to Project and we go to Edit Circuit Appearance. Now you see that I've actually already created most of this one. I just need to adjust the pins. So this is going to be our X in pin, and this is going to be our Y pin, and we've got our float, and we've got a round, and we've got our output pin. So this is a little block here which I've called Exponent. So what we can do is we can get into the main section, we can get into the multiply section here, and we can add in an extra section here which we'll call Exponent. So Control C, Control V, and we'll just put this down as a heading, and that's going to be called Exponent. And we can drop down our new circuit, which is going to be FPU underscore exponent. Now there's going to be a connection here to float and round that come from somewhere else. So in order to run a simulation here, we're going to just have to tie these to a particular value. So right now what we're going to do is we'll take the float and we'll tie the float to a value of 1. Now I'm doing it to a value of 1 because I know that whenever we use the numbers that we're going to, as an example, to multiply, then those numbers will give a value of 1 for this float. Okay, so it's just a bit of hindsight here that allows us to run through this example. And this end here, the round is going to be a value of 0, so there is no rounding all the way up into the exponent, so we can stick this constant here, and it's 1 bit, and it's a value of 0. So that will allow us to run a little simulation to give us the output here for the exponent. So we're going to have the value for the exponent coming in, so Control C, Control V, so this is the XE, I'll face it east, and we've also got the YE, again, which I'll face east. And then finally you get the output here, which I'll just call EXP. I'll have to face that west. I'll call it EXP. That EXP goes here. Now what we're going to do is connect the EXP up to the actual pin here. So that's the exponent pin. Control C, Control V, and I'll face that north. And you can see it's actually already started reading through the bits here. So let's go ahead and we'll actually do the simulation using the figures that we have for the example, and we'll see whether we get the correct output for the exponent. So we're going to put the value of 1 in for the sine, and we're going to put this value in here for the exponent for x, and we'll put 0 in for the sine for this one, and this value in for the exponent. And if it works out okay, and whenever we multiply it out, we should get 1 out for the sine, and we should get this value here out for the exponent. And we can see these values actually down here. And we know that we're going to have 126 minus 127, which gives us minus 1. We'll have 135 minus 127, which gives us 8. Whenever we add both of them together, we'll get the value of 7. But we know we're going to add on this floating point, which is going to shift it by 1, so we'll actually get a value of 8. And then whenever we change the value of 8 into the final version, we're going to have to add 127 to it. So we're going to get the 127 plus the 8 will give us 135. So let's go ahead and we'll have a look at that in the Logisym. So these are the values here which I've put in, which are going to be 1, 0 and all 1s and the zeros. Now we don't add in any of the mantissa, there's no point because the mantissa is not connected, these are all just x's, so the last 23 are just x's, meaning don't know. And we've got the other one, which is the y value, which is the 0, 1, 4 zeros and 3 1s. Now whenever we multiply those together, at the output we get 1, 1, 4 zeros and 3 1s. And this here is actually the number for 135. So let's have a wee look down in, so it does work. Let's have a wee look down inside the actual circuit itself, and we'll put in a few values here so that we can see. So I can see I've already added these ones here. So we've got the 126 for the x, we'll get the 135 for the y. We take the 127 off, and if I change this here to a sign decimal, you'll see here we get the minus 1, and if I change this one here, it's already a sign decimal, so you're going to have minus 1 plus 8, so you're going to have a value of 7. So that's what we were expecting to see, a value of 7. But we've noticed that we've also added in the 1 for the float, so that's going to take us up here to a value of 8. So if I put a little probe in here, and you'll see it's got the value of 8, and I just make that unsigned decimal, and we add on the value of 7f, which is the 127. So our final output here is going to be 135. So that's what we see at the final output. If we go up to the top level, the final output here. So this does work, and that's us done the exponent part, but as I said, it's not completely finished, because it turns out that this will only work for normalized numbers times normalized numbers. It won't work for normalized numbers times denormalized numbers, but that's something we'll look into in a later video. We'll go on in the next video and we'll work through the mantissa, and we'll work through the rounding and the float, and we'll pull it all together. So thank you for listening. I'll get you in the next video. Goodbye.